Good morning, everyone. What's up today? Okay. So, doing well. Thursday, and currently the Chapter 15 assignments are due today. I have added the Chapter 16 assignments. We haven't officially begun those, except for talking about capacitors in the lab. So the current date for those is next Thursday, but I'm likely going to change that because, let me pull up the calendar real quick.
You want to class Tuesday?
Yes, because it's assessment day and because everything's weird, I'm just going to call that we don't have anything next Tuesday. I'm going to go ahead and tell you guys that, rather than worry about who can make what. I don't entirely know what everyone's doing on assessment day because I don't have any assessment day related to activities, but just to go ahead and say for the record, we won't have class or lab next Tuesday, March 16th on assessment day. Just to avoid any conflicts, and additionally, this whole semester we're just blitzing straight through the months without many breaks in between, so I think some rest occasionally is warranted. Yes?
Wait, so no lab that week?
Well, probably yes, because the next lab I'd like to do would involve resistors, and we haven't even really talked about capacitors yet. So, no class, March 16th, which is next Tuesday, and no lab next week. Any issues with these announcements? Okay. The week after that, we should be on track to continue on to Chapter 17 and start talking about resistors and circuits and all those good things, and we'll start doing some more circuit-based labs where we're actually combining resistors together and measure those, because I know those work.
And you said the chapter 17 was due Thursday, but we might move it and then move it up or move it back?
Good question. So currently, this is just to show what's currently there. The Chapter 16 assignments are due for next Thursday. I went ahead and put them there to make it a week after a week after today, which I moved the 15 assignments to. But, if we start Chapter 16 today, I'm thinking I'll push it to this Tuesday, next time we meet, the 23rd, so that we would have today, tomorrow, that day. I guess we'd have 4 lectures. but not all of my classes would. So I may end up moving it to here so that all of my classes can have enough lecture time with it. It's my other class, so it's twice a week and it's kind of wibbly wobbly.
So you only meet twice a week?
They have longer
Oh,
sessions.
the hour 15.
Yeah, those things. Trying to keep one group on pace with the other in there. Apparently chapter 15 homework due tonight. Chapter 16 homework yeah, I'll just go ahead and make it due March 23rd. How about that? Official announcement. More time to do an assignment is rarely worse than less time. Any questions or issues with these announcements? Okay. So, the 15 homework is still due tonight. I've been getting still a couple more email questions about this particular assignment. So, I want to open up with the chance for you guys to, again, ask about any of those questions that you are having issues with. And we will then move on to chapter 16 material.
Can you look at 8? I did it, or that's the one I don't know why.
Number 8. Stay signed in. Sign, please.
But the total for because I hate changing patterns.
Chapter 15, homework review. Number 8. Why did you? Okay, so let's paint a picture together, because that's going to be important. Please have ink. Marker. Okay, so number 8. 2 metal balls. We have object A and object B. Go ahead and use red, because I know they're both positively charged. These two spheres are a distance apart and are connected down the middle by some length of string, by a taut non-conducting thread of 1.8 something. So you know whatever this, I call this R, because it is the distance between the two spheres of negligible size. So we know we have these two spheres, and we know how far apart they are.
Wait, why do you have a unit for the length?
I believe it's because the unit is ultimately just going to cancel. I don't have my notes in front of me, but I think it'll just cancel out on both sides.
Force is newtons,
Mm-hmm.
and then charge is. I don't know how it cancels.
It's okay. We will look at that together. So these two spheres are connected by a string, and we are told, we don't know exactly what their charge is, but we know A is positive Q, and B is positive 2Q. So whatever these charges are, we know that B is twice as large as A. We know that for a fact. Maybe it won't cancel, but still might not matter. We are then told if the tension in the string is blank, so we know tension, what then is the magnitude of these charges? So physically what's going on here is, if these two orbs have the same sign of charge, if they're both positive, they're going to what to each other?
Repel?
Yeah, they're going to repel. That's not a trick question. They're going to repel, they're going to exert a force away from one another, and so the only thing keeping them from moving farther away from each other is the string. So the tension in the string is directly counteracting the electrical force, which means that ideally, the tension in the string should be equal to the electrical force. So by measuring string tension, we can estimate what the electrical force in this situation should be. So, the things that we know for certain are R and FE, and what we want is Q. We want to know what Q is. And by solving for Q, that will tell us what A is directly, and then you double Q to find out what B is. So with what we know, what formula do you think we should look at?
F equals K, Q
Very good. So that's FE times K, QQ over R squared. Now this is the generalized form where the two Q's are different to one another. In this specific situation though, since the two Q's are a function of one another, we can rewrite this as K times Q times 2Q over R squared. And those are both the same Q. So Q times 2Q can be further rewritten as 2Q squared. And I'm going to pull out my calculator real quick and make sure I can solve the versions on the board. Make sure everything evens out. So, I'm just going to rewrite this really quick. 2Q squared. So, our force electric is 1.5 times K, 8.99, 10 to the positive ninth, 2Q squared, the radius squared, whatever it is, 0, also squared. Okay, yes, this does work, and I don't know why it doesn't specify a unit on that length, but given the fact that everything works out evenly, I can only assume it's meters, since it calculates correctly with K and the rest of the formula designed to accept meters. It's probably just a typo on some poor intern's part, I don't blame them. They're allowed to make mistakes. We all are, we're human.
So for algebra wise, you would multiply by the radius squared to get to the other side,
Correct.
and then you would divide by 8.99 times 10 to the 9th and 2. Since 2 is with Q, you could just divide both.
Divide this over, multiply this over, divide by 2, and then take the square root. And I'm gonna write up what I got out of my calculator, because it's the same number, it's just in a different form to what WebAssign wants. Q equals 1.64 times 10 to the negative fifth coulombs. The formula will give you coulombs, and it will give you about this many coulombs. WebAssign is currently asking you for micro coulombs. Micro is the times 10 to the negative sixth prefix. So to convert, you move the decimal point 6 places, well, this way, which would cancel out most of this and leave us with 16 micro.
Wait, you moved to the left, you moved to the right?
Well, okay,
I don't know, because I just put in my calculator because it was too confusing.
that's fair.
That would be where I got it wrong though, because I got that same exact form that you're talking about, but I got that number and then that's why it's wrong.
Okay, so sorry. This is the number I just wrote.
Mhm.
I just put it out in its normal form. To convert to micro, 1, 2, 3, 4, 5, 6.
Got it.
Move to the right.
Correct.
But yeah, that explains why I got it wrong now, because I did the exact same thing. I got the number, but then I put that number and got it wrong. So that's why I couldn't confirm.
Whenever you are going from base to a smaller unit, the number should get bigger.
Wait, say that again, sorry.
If you are converting from the base unit, from coulombs, to some degree smaller, so like micro, then the number, not looking at the unit, but the number should get larger. So this, sorry,
Yes, yeah.
this, ignoring the unit, is technically a bigger number than this, ignoring the unit. Okay, so that is 8. Another question with a picture. It's kind of important and why I wish there was maybe more of them. Any other specific homework reviews? Okay. I believe between today and last time, we've talked about most of the problematic ones, so I feel comfortable with you guys with this particular assignment. But again, keep working on it. Send me any questions via email, or find me in the building as soon as you have them. Because if you leave it till like 2 p.m., then I'm going to be falling asleep and you're going to have to finish. Okay. Keep this tab open in case you guys think of anything while we're working today. Now, we're going to begin looking formally, lecture-wise, at capacitance. I've mentioned briefly what a capacitor is in lecture. There's a couple of examples of accidentally created capacitors, and I'll try to point out where applicable. And lab this week is also about capacitors, what they are, what they do, how they work in circuits. So this is the lecture side of that. So how to create a capacitor. Capacitor itself is a very useful electrical component. Whenever building circuits, any circuit, you always have various components and things. You ever taken a physics class where you've dealt with circuits and resistors before, you've seen lots of these elements before, you've probably seen circuit diagrams. If you haven't, you've probably seen circuit boards in sci-fi, if nothing else. And every single circuit is always made up of specific things. There's components wired into the circuit that allow it to function. And a capacitor is just one of those types of components that performs a pretty important task that I don't think modern society would be able to exist without that specific device. I think, no, it was a transistor where radios become tiny. Capacitors are very important though. The original touch screens work on a capacitive piece of technology, which then paved the way for our current touch screens, among other important things like TV vacuum tubes. So, what a capacitor physically is, let's say that we have a solid plate of metal on the left side that is positively charged. This positive object would technically be emitting E field in every single direction, so it would also be sending E field out on this side too. But since this is a solid object that is flat, whole objects, always exert field perpendicularly out of their surface. So if this was a single proton, which we consider to be round, it emits field in every single direction. Rather chaotically, we can't really control that. Things tend to start moving around in circles and off in different directions. It's a little chaotic.
We always emit perpendicular to the object.
To the object's surface, yes. You know what, let me backtrack real quick. Let me dig up those notes. I'm real quick going to pull up some pictures from the chapter 15 notes that show fields being created perpendicular to their surface, to the surface creating them. Okay. Showed a couple of these pictures. This is one where we've got two charges repelling each other. The field lines are repelling against one another. But closer to the charge sources, you can see that these round objects are radiating field outwards, circular-like. But you can charge objects of all kinds of different shapes. You've got this inverted teardrop, kind of a balloony shaped thing, and this solid flat piece of metal, kind of like little capacitor drawings, what we're looking at. For the round object, it creates field outwards radially, like the other two point charges. But notice, as you get closer to the tip of the teardrop, as the surface becomes slightly more flat, the lines start coming out more parallel with one another. Instead of all going off in slightly different directions, they're becoming more parallel. And they're really parallel coming out of the completely flat object, or at least on the flat side. The round sides, things get more radial again. Similar kind of thing here, except the circle has no flat side. So as a general rule, E fields are emitted perpendicularly to the surface creating them. That's a general rule that I will put on the board. So, for this flat piece of metal, it's going to create E field lines perpendicularly outwards on all of its sides, but right now we only care about the ones going to the right. And so these lines are all parallel, they're all moving in the same direction, which makes things nice and easy to control. If we dropped a proton in this field, we know it would move straight line this way. So you can kind of use this like a little electron cannon or proton cannon. The old gold foil experiments where I think it was Rutherford fired protons into gold foil to see what would happen. Those protons were accelerated using something like this. So this field points to the right is uniform in strength, or rather, it's specifically uniform at every point that's the same distance away from the plate. So if you were to draw vertical lines here, everything here would be the same E field strength, everything here would be the same E field strength. This plate by itself, the field would still get weaker the further away you go, but it'll be the same level of weakness at every point that distance away. I'm actually going to move on real quick, because having one plate that is positive by itself will only get you so much. To create a capacitor, we take a second plate and make it negatively charged. This field would work much the same as the positive plate, except pointing in the opposite direction. Same principle, all the field lines are parallel to each other but perpendicular to the surface that made them. The field gets weaker the further away you are, uniformly so, and stronger uniformly the closer you get back to the plate. This gets interesting when you put both of these plates near each other. They should ideally be parallel to one another, and when they are, you can create an environment where the E field is always pointing in the same direction, and where the field is constant throughout the entire device. One plate by itself, the field's going to get weaker the farther away you go. But as long as you are between the two plates, the E field stays the same in this scenario. Because if we drop a proton right here and it drifts away from the positive plate, it's going to drift closer to the negative plate at the same rate, which will keep the net E field in the middle constant the entire time. So it doesn't matter where you are in a capacitor, the E field stays the same. Which is very handy, because that doesn't happen in nature very much. So this lets us create an artificial environment with a specific known constant about it. And in physics, we like when things are constant because it's a pain calculating them when they change. And so, physically, this is all a capacitor is. Two metal plates, one positive, one negative, parallel to each other, some distance apart, creating a uniform E field inside. In lab, the physical devices that I had on the table that were called capacitors, the actual thing you might have bought from Radio Shack when Radio Shack existed, to plug into a circuit, looked a little more like this than like two parallel plates. Kind of looks like, I think of it as a can or a piece of candy with two metal legs sticking out of the side. You can bend the metal whatever direction you need to. This doesn't look much like two parallel plates, but what engineers did is they made their two parallel plates. They'll usually put some material between them, like styrofoam, to keep them from touching, and then they roll it up and put it inside this plastic sleeve. So think of it as, I believe some places will sell these weird sandwiches that have been made and then spiraled and then cut into slices again. And now they're just kind of helix shaped. You can see the spiral of whatever was the filling of the sandwich. It's like that.
Do they have to be touching the one plate with like the both ends of the plate? Because like I know in this capacitor it's like a spiral, but in other capacitors like that was just like a flat sheet. It didn't need to be touching. So does that like change the effect of its capacitating ability?
That is a good question. So every capacitor, whatever shape it is two plates separated by some distance. They can't touch. If they were directly touching, then because if this one's positive and this one's negative, if they were touching directly, electric current would just flow from one to the other. The only way we get this constant effect, well, I get to actually say what capacitors do in a circuit, why we're interested in them. They store electrons. Electrons enter the circuit, they get stuck in one plate, they begin slowly traveling through the E field to get to the other plate. It's called a capacitor because it has a certain capacitance for storing electrons within itself. It's kind of like a battery. We have used capacitors as batteries before, to some degree. So its purpose is storing charge within itself. And if the two plates were just touching, then that defeats the purpose because then the charge could just flow directly from one side to the other, and you might as well just use the wire instead. So this only works as a capacitor if they aren't touching, which is usually why engineers will put some neutral, very thin material in between the two plates to keep them from touching even after it's rolled up into a can. But if you were to open this up and unroll it, you'd have your two plates, you'd have the material between them, and one wire would connect to one plate and one wire would connect to the other. So each of these two legs is connected to one of the two plates.
Wait, you didn't answer my question.
Oh, sorry, what was the question?
So does the fact that it's rolled up or that it's flat affect its ability as a capacitor?
I don't believe so. The factors that affect a capacitor's capacitance include the surface area of the plates and how far apart they are. So as long as, like, rolling it up into a tube wouldn't change the plate's surface areas at all, and as long as you have sandwiched that constant uniform piece of styrofoam in the middle and rolled it up evenly, the plates should remain a constant width apart the entire time. You might need to layer it with more and more foam to keep one plate from doubling over and touching itself. But as long as you do it right, it should still work fine. That said, this is why engineers will design it, calculate it, make it, then roll it up, and then double check what its current capacitance is, and write that on the side before selling it. Since I've talked about it briefly already, a capacitor's function it stores electrons and electrical energy inside of the E field between the two plates. Its ability to do so, like the actual measurement of a capacitance's ability to function well, is called its capacitance. Like the effectiveness of a battery is measured as its voltage, the effectiveness of a capacitor is its capacitance. And the unit for capacitance is farads. The variable is capacitance, which is abbreviated to C. The unit is farads, which is abbreviated to F. So C is measured in F. This is the same name as a scientist named Faraday, the man who the Faraday cage is named after. And we will look at this particular formula a little bit later, but the actual things that determine what one capacitor does versus another are the area of the plates. Usually the more area, the more charge they can hold, the higher the capacitance. The width between them, the farther apart they are, the slower the whole thing is. So typically that makes it a weaker one. But also what you jam between them matters. Certain materials just resist electrons traveling through them and resist E fields traveling through them. So if you were to shove a rubber sheet between the two plates, you'd be neutralizing its ability to function pretty well. Meanwhile, if it was just aerogel, which is practically nothing, it'll go on. That material, the word for that material is a dielectric. So what you put between them to keep them from touching does affect it.
Wait, must be a dielectric, like that, or it's called a dielectric.
Whatever material is in there is called the dielectric. And even if there's nothing in there, there's something in there because we live on a planet with air. So air can function as a dielectric.
Which allows electrons
To travel, yes. If you did create one in a vacuum, like in space, vacuumed out, it would be a lot harder for the electrons to actually move. So air is a better conductor than a vacuum. So it's good that air is there.
to, like, vacuum is nothing.
A vacuum is nothing, and that means there's no atoms for the electron to leap across. Electrons very rarely will just jump on their own by themselves through the void of space. They need something to conduct through. Which is why we don't get the sun constantly blasting the universe with electrons. Which is good, because it's enough that the sun is already emitting fire at the entire universe. We don't need to be throwing lightning too.
Wait, does that mean that the best, the best way to be protected from the sun is to wear something like rubber?
That would protect you from the charge of the sun. This particular rubber would need to be, I don't know what kind of rubber could resist the temperature of the sun.
One that has air conditioning with it,
There's a reason we haven't scheduled a flight to the sun yet. We don't have anything that can withstand that level of temperature and the charge of the plasma that makes up the sun's upper atmosphere. One day, maybe. Right now, yeah.
Are there any other planets that are like opposite, like they're too cold and have a charge, or can you be cold and have a charge?
Well, Pluto's an ice ball.
Or like is the charge affected by temperature?
Yes,
or does charge have temperature? Or does it create temperature?
these are all excellent questions. I'm going to turn your attention to light bulbs for a second. Electrically speaking, when you turn on a light bulb, and I'm just going to draw the old school incandescent ones. That's a terrible bulb shape. It's a little better. You've seen this thing in there before? This is the filament. And what happens is when you screw the light bulb in, current comes into the bulb, travels through the filament, and then goes back out. As it's traveling through the filament, when electricity travels through anything, it leaves energy behind. Electricity always leaves energy behind in whatever it travels through, which is why batteries eventually run out of charge. Running current from a battery through a circuit literally uses up the energy of the electrons, which is why the battery drains eventually. So energy is entering the bulb from the electrons, which means as the current passes through the filament, it literally leaves energy in there. And that energy is what makes the filament glow, because it increases the filament's temperature, and when tungsten metal gets hot and stays at a constant temperature while it's hot, it glows. So electricity has a tendency to make things warm, because electricity leaves behind energy, usually as thermal energy. I don't think running electricity through something can make it colder, but it will make things warmer.
Is that why the light bulb is hot when you plug it?
Uh-huh.
Like if you leave it on for a while?
Additionally, the sun is an interesting case because it's mostly made of plasma, which is air that's been made so hot, its nuclei are vibrating so fast, they've literally torn free from their own electrons.
What? Wait,
Plasma isn't just hot gas. It has its own unique properties. It's so hot, all of its electrons and nuclei have separated, and they're now buzzing around separately from one another. This is why plasma has its own bizarre glowy, soupy behaviors. And it's also why the sun is both hot and electrically chaotic. So therefore, the colder something gets, the more electrically stable it gets. So no, approaching Pluto, I don't think electrons are going to be an issue. The freezing to death will be, though.
Right.
I got traumatized as a kid by that Magic School Bus episode when they were exploring the solar system. They went to Pluto, and because Arnold was mad and wanted to prove a point, he took off his helmet and turned into an Iceman. He got better, though. Still, scary things for an 8-year-old.
The scariest episode of Magic School Experience when he ate those snacks and turned orange.
Oh
And it freaked
my
me out,
god,
and
that
I'm
one
never
was
gonna eat carrots ever
creepy.
again.
Oof.
Because
I
it's
don't
like,
remember that one super
it was
well.
like he ate like some kind of carrot snack and had like some kind of like thing in it, and it turned to orange.
Like the pigment or something. Yeah, I remember.
And I was
Whoever
like,
wrote that episode must have watched the Oprah episode where the man turned blue.
I was like, no thanks. And when they were inside the body, that one was kind of weird.
Well, that's true with like if you eat a lot of carrots, your like palms and feet get like orange tinted.
That's why I don't eat carrots. So no.
I really like carrots.
Are your
It's
feet
kinda like-
orange?
Not to my knowledge. Okay, we're nearing the end, so I want to at least get a formula for your use today. Capacitors store charge, but they also store energy. Like I said, this is basically the earliest battery ever invented, electrical battery. And electric fields work a lot like gravitational fields in that they exert forces on things that also create those fields. And objects try to move from an area of high potential within a field to an area of low potential within a field. In a gravitational field, objects move from high GPE to low GPE. It's the same in an electrical situation. If this is, there goes my styrofoam orb. It's not an orb anymore. In this particular field, if you drop a proton next to the positive plate, it has high potential in that area. It doesn't want to be there. If I was holding it still, forcing it not to move, it would have a lot of energy trapped inside of it from the field around it because it doesn't naturally want to be here, like how anything doesn't naturally want to be up here. Left to its own devices, it will go anywhere else, or rather, go anywhere down. So in this spot, the proton has a lot of potential energy, and if I release it, that potential is going to turn into kinetic energy as it zooms across. An electron would actually do the opposite. The electron would have higher potential over here because it doesn't want to be near the negative side, and it would zoom over to the positive side. But for either particle, it has high potential on the side of the same charge and low potential on the side of the opposite charge. So, this is a work function. This is work. The E field is doing work on these particles because it exerts a force on the particles as it moves some distance.
Wait, you said the high potential energy turns into kinetic energy?
Correct. So I actually want to look more at this particular part of it, more so than the last line. The change in a particle's potential energy going from one side to the other is equal to negative times its charge times the E field in the capacitor times the distance it has moved from one side to the other. So as you go from one side to the other, your potential energy is going to drop as your kinetic energy rises.
So decrease in distance, decrease in potential energy, which makes sense.
The farther it drifts away from the plate it doesn't want to be near, the less potential it has, the more kinetic it has. And electricity is mostly just electrons with kinetic energy moving. So, because these particles are stored within the plate, the energy here is also stored within the capacitor. The energy is also stored within the capacitor. And it's, nope, that's officially timed, so I don't want to start an example we can't finish. We will pick up here tomorrow. Be prioritizing chapter 15 homework tonight. Send me any questions you have. We'll continue with 16 material and how we're going to use this tomorrow. Any questions right now? Okay. Have a good day. Remember various announcements. Finish your 15 assignments tonight. And do have a wonderful day.
Wait, so what? Like, okay, electricity is a flow of electrons. So what potential energy was converted to kinetic energy for electricity to flow through the light bulb? But what kinetic, potential energy was there? Like, what do they have to allow that flow? You know what I mean?
Well, when you drop a proton next to a positive object, it now has potential.
But is that what's in the light bulb? Or like, how is that happening is, I guess, what I'm asking.
Well,
Or like, in your circuit thing? What are your outlet?
right. For a circuit as a whole, I'm just going to draw one using a T-cell battery here. One end of the battery is positive, one end of the battery is negative. So, on this side of the circuit, a proton, there's a high amount of positive potential over here, and a proton doesn't want to be here. Meanwhile, on the negative side of the battery, there's negative potential where the proton would rather be.
So that means that electricity always flows this way?
Always, yes.
This way. But it has to be electrons.
And this is why I dislike electricians. I dislike some of the nomenclature here, because electricity itself is always moving electrons, and yet we've defined everything from the proton's perspective. Electricity isn't made of moving protons, and yet we draw our diagrams and make it and treat it as though electricity is going to flow from positive to negative. A proton, somehow in this circuit, doesn't want to be here, so it's going to move away from where it has high potential through the circuit to where it has low potential. The problem is, it's not protons moving, it's electrons. So what actually happens is, electrons go from here to here.
See, that makes more sense.
I'm glad, because that's what actually happens.
Then why?
I don't know. I didn't write the textbooks. The people who first invented this map just decided everything's going to be from the proton's perspective.
Yeah.
Thanks, Faraday.
I mean, either way, it makes sense though, because you're positive to negative, like you're not going positive to positive. I mean, you know.
But if you were to wire in a light bulb, as long as it is wired into the circuit and there's one solid path for the current to follow, the potential still holds. The electrons will just travel through it to keep on going to the wire.
That makes sense. Okay. Thank you.
You're welcome.